the question is to find a map, a one-to-one map between the quaternions and the SU2 generators. And the quaternions have some algebraic relations that we are given. And the first thing that I thought of was to try and see what relations the SU2 generators fulfilled. So just trying the same products, and we can use a formula, so it goes a little bit easier than to use the direct matrix multiplication. Then we can see some similarities. So the quaternion I is somehow related to the first Pauli matrix, and J to the second, and so forth. And the one thing that differs is a factor of I on the right-hand side between the two maps. So we could guess that it should be a factor of I that matters. But maybe it's a little bit more general to make an ansatz where we think that they are related linearly with a constant that is allowed to be complex. So if we try this map or ansatz, we can compare, for example, that the quaternions ij should be equal to k, then sigma 1 and sigma 2 with their constants should be equal to sigma 3. And then we use that sigma 1 times sigma 2 is I times sigma 3. And then we get a relation between the constants. And we can do this also for the other products. For example, k times I should be equal to j. And if we combine this information, we can see that C1 should be equal to plus minus I. And you can do this also for the others.
So I have a question. So that I would conclude from squaring the elements to minus 1. So the quaternions should square to minus 1, but the sigma square to 1. So from that alone, I would conclude that the C must be plus minus I. But as I understand it, that's not what you used actually.
Okay. No.
No? Okay.
Yeah, I was suspecting.
But you check it in the end instead. That's also fine. Yeah. Okay.
Yeah.
Come on.
Yes. So if we use this, it should actually fulfill these I times j should be k, ki should be j, and jk should be I. But then we have another relation that the product of these three should be minus 1. And then we don't know if it should be plus or minus for the constants, but we get this equation. And we can check that with these three constants equal to minus I and C4 just equals to 1, it is actually fulfilled. And then there is just one more equation that's supposed to be satisfied, and it already checks out. So yeah, that's one way to see that the map or isomorphism that we are after is this one.
Okay, yes, good. So the strategy here was to make an ansatz and to get some constraints on the constant relating the sigma matrices to the quaternions, and then you figured out that the constant must be plus or minus I, and then actually to have the representation squaring to minus 1, you figured out the value of the constant to be minus I. Yes, I think that is entirely correct. It is though quite different to my approach to this. So maybe there's someone else who had some other approach and maybe even got some different answer, because it's not one answer, there are multiple answers that are correct.
Should I stop sharing then?
And now you can, if no one else wants to share us, it's good if you have your material. It's better than nothing, I think. So no one else had any other solution, or did they did it in a different way? No. Okay. So I didn't know the answer to this myself, but my approach was to say that, okay, the element should square to -1. So if I take I times the sigma matrices, that works out. And then I thought the rest would work out automatically. It turns out that it didn't, because I got the sign wrong in the relation ij should be equal to k, for example. I had an additional minus sign there. My way of fixing that was not to introduce another minus sign, which clearly also works, but to swap the order of the sigma matrices. So I chose to swap sigma 1 and sigma 2, then they still square to -1 as they should, and I have an additional sign in the commutator. So that works. And instead of changing sigma 1 and sigma 2, I could have taken any odd order. That should also work. And here it's instead solved by introducing a minus sign, which clearly also works. So there are several maps that give the right answer. Okay. With respect to the quaternions, I can say that I very rarely encounter them. Pretty much never, actually. But nevertheless, I think they deserve more attention. The reason for that is that they are sort of the minimal representation of the interesting properties of this SU2 algebra. So instead of carrying around 2 by 2 matrices for which we have to treat 4 times 4 entries when we're going to square, etc., or we memorize the relations for the Pauli matrices, which is easier, but the most economic treatment would be to use the sort of 1 by 1 quaternions instead. But nevertheless, that is not what people are normally doing. I have heard, though, that they are actually used for fast computations, because they are related to rotations in 3-dimensional space. And indeed, actually, they have their origin from Hamilton and Hamiltonian mechanics and rotations in 3D. But surely they should be relevant for anything connected with SU2. And SU3 is a few copies of SU2 and some additional relations, so I don't know, possibly there as well. But I never see them, so I thought it was an interesting question. So, okay, but I think that's about what I have to say about the quaternions. They didn't used to be part of the course, but I think they fit in quite well. Then the next problem is a fairly easy problem. And maybe someone in group 4 has solved it. I think that should be the case.
I can share screen.
So will anyone present a solution to problem number 2?
What the hell?
So maybe I'm sharing the wrong window.
Yeah. What the? No, I shouldn't share that. Okay, how do I get back to Jesus?
So if you stop sharing and start sharing the window you intended to share, alternatively share the screen.
Do you hear me?
So now it's the screen, general screen share.
Hello?
Yes, we can hear you.
Did you hear me?
Yes, It's not perfect quality, but we can hear you.
Oh, sorry. Like so. Okay. Can you still hear me?
Yes.
Okay, perfect. Okay, so problem 3, yeah, this is your exercise. Okay, so first we're supposed to have a look at this, calculate one of the structure constants using this Gelman representation. Okay, so if we go to our document here, so simplest way is, okay, we want to, as the problem said, easiest to do is 1 to 3. So we try and commute the commutator for 1 and 2. And we get this and this. If we use the explicit matrices, yeah, it turns out that we get 1 T3 and then another T3. And then we say, okay, this structure constant is 1 as we expected. So not much to say there.
No, not so much to say. I would have done it in a bit fewer lines, but just noting that I have the sigma matrices in the upper 2x2 block, and I know the commutator of the sigma matrices already.
Yeah, exactly.
Then I don't have to write out the matrices explicitly. But anyway, it's.
I didn't typeset this, but that's what I did as well. Yeah.
So we only have something in the 2x2 block, and then we essentially have sigma free, and that happens to be essentially T free, and it's just a matter of identifying the constant, which happens to be 1 here. So that was an easy exercise to see that you have some idea what's going on. And then there was a part B. Are you going to present that as well?
Yeah, exactly. I will do the rest now.
Good.
So, okay, and then the next question was, okay, what happens if the generators were normalized to be a factor 2 larger? And of course you can use the explicit matrix form if you want, but I don't think that's very nice. So you can just calculate this commutator now, but multiply this by factor 2. Okay, then you see that this is 4 times this, and then you get this relation. Wait, what the technology, for God's sake. Yeah, you get this relation, and then of course you see that if you write this in the same form as if this is supposed to be without the factor 2, we can move this factor inside here, and then we see, okay, then this structure constant should be twice the old structure constants.
Yes.
So not much.
And of course you generate the same group if you multiply all structure and all generators by a constant. So occasionally you see the same group with different structure constants because you can just change the size of your generators. But that can be confusing because on the other hand, you often hear the statement that the structure constants define the group. And as we have seen, we can clearly change the normalization of them. We can also take different linear combinations of the generators and we still generate the group. So in that sense as well, it is confusing to say that the structure constants define the group because you can change the structure constants.
Would it be more right to say that the proportions between the structure constants define the group then?
That is actually also not true because you can take sigma 1 plus sigma 2 as one of your generators and sigma 1 minus sigma 2 as another generator. Yes, and you will still have different structure constants. But that was a good question. And I think it's not much different than if I have a coordinate system and I know everything in that coordinate system, I know everything. But I can as well pick another coordinate system and I have completely different coordinates. And I can pick non-orthogonal coordinate systems, etc. Okay. So that was exercise number 3.
Mm.
And then we have exercise number 4, which is about the quadratic Casimir operator for SU2. So did anyone in that group solve that problem as well?
Yes, I will show my solution as well. So, okay.
So maybe actually, since this is supposed to be for the benefit of all the students, I think there can be a danger in that it's too quick to take notes, the speed in which you're presenting. So maybe you can think about being a bit slow when you present it.
Okay, sure. So the first problem here, we're supposed to use the commutation relations to show that C, this Casimir operator, commutes with all elements in the algebra. So let's go to our notes here. Okay. So first, we simply calculate the commutator between C and some element in the algebra, lambda I, and then we want to show that this is 0, because if that holds for any lambda I, then it holds for all elements. So then we have shown what we wanted to show, and then yeah, we just removed the factors in front here. They won't make a difference. So just for cleanliness. So then we can just simply write, okay, C is the sum of the squares of all the elements, lambda I. And then we can, of course, move this sum outside. We get this. And then we can use the, I don't know if you call, not the Jacobi identity, but property of the commutator, that we can move one lambda k out here, and then we can move it out here. And then we have these two. And then we know for SU3 that we have the following commutation relation between the elements in the algebra. So then we can just plug that in here. So we have lambda k, lambda I. So we'll get lambda k, lambda j, then sum over this here. And the same thing here. And of course, we can move this sum over here. And then we see, well, this, maybe I can use this instead. Yes. So this here, of course, we see that that's the anti-commutator. And important to note is, of course, the anti-commutator is symmetric. So we end up with this expression, but then we see here that here we sum over k and we sum over j. And here we have k and here we have j. And then we can use the fact that this structure constant is anti-symmetric in all its indices. So when we sum over this, maybe one time we will get k equal to 1, and then another time we will get k equal to 3, and then other way around we will get k equal to 3, j equal to 1. And this will exactly cancel each other. So we get 0. So we have shown that this commutator is 0 for lambda I, but of course this was for an arbitrary element, so this holds for all elements in the algebra. So we showed what we wanted to show.
Yes. So at some point it stopped. It sounded like you took a particular lambda I, but you did indeed only take an arbitrary lambda I, and you showed it in general. So it works in general. And then notice that it's the anti-commutator that you have standing there underlined in blue. That's of course entirely correct. I would not have written out that it's the anti-commutator, but I would just have noted that the expression itself is symmetric in J and K, whereas the F is anti-symmetric in J and K. So in just knowing that, it vanishes, but yeah, sure, you can write it as the anti-commutator if you want. So thanks. I think it was a good and clear solution.
Mm-hmm. And then we move on to number 2. So in the number 2 problem, we're supposed to, maybe I can clear all drawings. Yeah. Perfect. Okay. We should argue that this holds for every SUN, i.e. summing over square generates with a Casimir operator. And then we are supposed to use that the structure constants are fully antisymmetric for SUN. Okay, well, we simply note that all we need for this to hold for any n is that we need to have the same commutation relation, because then we can simply reuse the same argument as above, and then simply writing our new C as the new sum over squares of all the elements in the algebra. And then the only thing we really need is that these are fully antisymmetric. Well, we know it was given that we know that for SU2, the algebra, the structure contents are fully antisymmetric. So this sort of argues that it should be also the case for all n.
Yes, that is entirely right. So it was actually a pretty trivial exercise. It was just noting that you didn't actually use the design lower rate generators, but you just used the antisymmetry. And actually, we have already seen this problem in the SU2 case. Then it was L squared and Li. So that was on the first exercise sheet. And then we have yet more subtasks for this problem.
Yes, so we have task 3. And then we are simply supposed to calculate the value of this C given these Gell-Mann matrices that we know. And I didn't think it was necessary to write out you will see that if you calculate the square of all these matrices, of course, there are a lot of them have sigma matrices in them, and they will just, well, when you square them, you will get some diagonal matrix. And when you add them up, you get this. So not really interesting. Maybe interesting to note that, of course, I think it should be diagonal or proportional to the identity matrix to make sure that Schur's lemma holds in some sense.
Yes, so indeed it's not difficult. It's just a matter of calculating right. And the generators essentially have sigma matrix. Many of them, all but one, have sigma matrices scattered over a few places. And then you can just use that the sigma matrix should square to 1. And that 1 will then be a 1 in the 2 out of 3 rows and columns that's taken up by the sigma matrix in question. So you will have 1s in the 1 and 2 positions on the diagonal, or in the 1 and 3 position in the diagonal, or in the 2 and 3 position in the diagonal. And what more? The last generator is diagonal, so it is trivial to square it. And then, so Daniel, you're one of the engineers, is that right?
Yeah, that's correct.
Yeah. For those who are more interested in particle physics, this factor is a bit famous, and it's the CF factor that you may encounter in QCD. But it connects to the last sub-problem of this exercise. So let's see what's to say there.
Yeah, so we of course we're not that comfortable with particle physics, but we gave it a go. So I can show you what we arrived at. But if it's completely off, maybe you can just stop me.
Yeah.
Yeah, perfect. Okay, so let's just state the problem first. So we're given this fact that we can interpret these Tij terms as a quark with index I entering some vertex, and then a quark with index j exiting the same vertex, and then interacting with some gluon A. And then we're supposed to argue that somehow this Casimir operator is, as you said, the relevant color factor for the self-energy diagram in quantum chromodynamics, where a quark emits and absorbs a gluon. Okay, so let's see what we got. Well, first maybe we state some some obvious properties. So firstly, we want to sort of use the hand-waving fact that this matrix is diagonal, and somehow that should relate to a quark emitting.
You mean not the ij, but the sum of them squares?
Yeah, exactly.
You had your pointer over the TIA when you said that it was diagonal, and it's not
sorry.
Yeah. You mean the figure.
Yeah. So we have this factor Tij, okay, and then we know that from the previous exercise that when we square this and we add them up, we get something diagonal. Well, every component there is a diagonal matrix. So the square of this is some diagonal matrix. Okay, and then we look at the indices for this. Well, we have square root of this Tij. Well, this of course is this proportional to this, contracting over k. And then I've inserted a delta function just to indicate that it's diagonal, but it's not really correct to write it like this. But in this way, we end up with this. And here we sort of see that if we have this interpretation, we see that we have some quark entering this vertex I and interacting with a gluon A, and then some exiting intermediate state, I guess you call it, K, and then another vertex where K enters and the same quark index goes out and interacts with the same A. So that's sort of, I guess that sort of makes sense. And of course, the total matrix C is then the sum where we sum over all these A's. And I guess we have 8 types of gluons, or there are 8 independent color states in quantum chromodynamics. And there are also 8 elements in the algebra. So in some sense, we are summing over all the possible contributions from different gluons, I guess.
Yes, indeed, the gluons are the different, correspond to the different A's there. So you have exactly the diagram that you have drawn there with the red gluon.
So I interpreted that like that we can take this first factor Tij, and we can interpret this like this diagram, like the basic diagram in one of the basic diagrams in QCD. So we have one quark coming in and then another quark coming out, and then A. And then if we multiply them together, we sort of get 2 vertices, and then we have this intermediate state that we sum over, and then this gluon that connects with the same quark.
Okay, so I think maybe the idea is roughly correct, but I think it looks like you're using what you want to prove. So you have assigned the same index I on both the external legs there, and it will be the same.
Yeah,
but you should prove that it is the same. So if you go up, so you have this generated Ta square, of which you want to take the component Ij. Let me see, then you write it out as Ta, and you introduce a dummy summation index K in between there. That looks right. And you take the component Ij of it, but the delta function should simply not be there, as you noted.
Yeah, exactly. But we know that it's diagonal.
Yes. So yes. So I would. Let me see if I can actually. Can you make this a bit bigger? Can you annotate it the way I would have changed it? It's maybe better than saying in words. So see, now I will use a different drawing tool, so I will be probably less precise than before. So I would not have had this delta function there, and then the second index would have stayed a j there. And then you have calculated that this whole matrix is some constant 3/4 times the identity matrix, 3×3 identity matrix, of which you can then take components I and j. Now, taking components I and j of this matrix is then just gives us a delta ij. So this is then 3/4 delta ij. So in this way, one has then derived that the color of the incoming quark, say I, red, green, and blue, must be the same as the color of the outgoing quark, say J, red, green, and blue. So if you scroll down, I like to draw this in your picture as well. So of course, unfortunately, yeah, that's keep it there. That's a good position. So the drawings stay on top, but let me also, because I'm not drawing on his paper, but on a different layer. Let me also try to draw this in the context of the picture. So here, the first vertex then, the gluon is called A, so there's a TA, and then the incoming quark is I, and the outgoing quark is J. So this is the color factor of the first vertex. The second vertex then has a similar color factor. It's the same gluon, A, it is A. There's an incoming quark which is, sorry, I should have gone a K in the previous place, because you call it K there. I-K, then it's T-A-K-I. And now this is the expression that you had. So this is the expression that you had. Sorry. Oh, this should have been a J. It should, because you should not assume that we want to prove that they are different. So now if you go up to your expression, very before. Yeah, perfect. We actually, if you go down, so the green is where it was originally, so where the scribble is exactly as our delta ID. So now there's a normalization factor of 2 between the lambdas and the t's, but ignoring that, we have exactly what I have written. So this thing here is then exactly this thing here. Of course, it doesn't matter what the dummy summation index is called, but it happens to be called the same thing here, K. Also doesn't matter what A is called. Yeah, and we see that it's proportional to the identity matrix with this factor CF. The factor CF, actually, we will see in the next exercise sheet that we can derive it in a more elegant way. It's actually a longer derivation, but it's a more general derivation that holds for NEN. So it's to derive what's in QCD known as the so-called Fitts identity that shows color conservation. It will be a more general derivation. Actually, the same quantity can be derived in yet another way that is SU3 specific and is using the ladder operators of SU3. So just as for SU2, we could write the Casimir operator also in terms of ladder operators and NJ8Z. One can also use a similar expression for SU3. So there are actually 3 different ways of deriving the same quantity, and this was the easiest one that didn't require so much understanding, where it was just squaring the matrices. Do we have any questions or comments to this? So I think, yeah. So I think this means that all the problems except the first one was solved. Now in the limit time I had to look into this, I by accident, I mainly looked into the other problems. So I would then suggest that we take the break already now, and then we meet at 15 past again. And in the meantime, I'll spend a little bit of time preparing to present the first problem, unless you have more questions to the problems already presented. Okay, so then I suggest that we take a slightly longer break than normally and meet again at 15 past. So hello again. So I had a look at the solution, but maybe there's someone who wants to present at least the first part A. I think Nicolina she could possibly do that. Is that right?
Yeah, I can do that.
Yeah. So I guess you want to share a screen or something?
Yeah.
Yeah.
Okay, do you see it?
Yes.
Okay. So the problem was we have an SU2 group and consider the tensor product of two j equals 1 irreducible representations, and then we have to compute the Clebsch-Gordon series graphically. So I start here by drawing a line down at the bottom for the first j equal 1, and then I draw the three different j prime equal 1, where I center the zeros around the values here down for the first j. And then I can see that I get 1 kind of -2, and then 2 -1, and 3 zeros, and on the symmetrically over here. And then I can kind of separate those out. So we have 1 2 state, and 1 state, and 1 0. And so this means that the tensor product can be represented as this, or the direct product can be represented as the direct sum of these states. And down here, I've just double checked that there are the right number of states in both representations. Yeah, and that's what I have.
Yeah, good. So you have then proved graphically that the 1 times the 1 representation gives you 1 spin 2 representation with 5 states, 1 spin 1 representation with 3 states, and 1 spin 0 representation with just 1 state.
Yeah.
Yeah, good. That's right. So my understanding then was that no one wanted to show the rest of the problem. It's not the easiest problem in the sense that it takes some computation, but it would have been useful if you had told me in advance. And actually, Nicolina told me, but it was too late that because I didn't see it until just before we started, that they didn't manage. So if you had told me in advance, I could have prepared a better presentation. But now it is. Now it is what it is, so I will then share my screen. Now, can someone confirm that you see my screen here? Great, thanks. Yes, okay. So the first part of the exercise, that's what Nicolina just did. So we find all the states graphically, and we double check that we have the correct number of states. And then already in the second task, we are required to do quite some work. So the task is to compute the reducible matrix representation for the SU2 generators and show that the Casimir operator J square has 3 distinct eigenvalues. And then we should interpret that in the light of the first solved exercise. Okay, and that takes a bit of work. So the strategy then would be to find J3 and to find J plus and J minus. And if we find J minus, J plus is easily obtained. And then to use the result that J square is in the particular representation is the representation of J3 squared plus J3 itself plus J minus times J plus. Okay, so let's now see how we would compute that. So first we have to find the representation of J3. So to find the representation of J3, we use this formula for the direct product. So we take first the direct product of the representation of J3 times 1 plus the identity times, that is O times, the representation of J3. So that should give us two matrices, one here and one here. And in the first matrix, we should take J3. Here, for convenience, I had a chance during the break to remind you about J3. And then in every element here, I should insert this here, this big identity matrix. So I have then a big identity matrix standing here, from here times there. And I have here a big 0 from this 0 times this identity matrix. And I have here a big -1 from this -1 multiplying this identity matrix. So the first part here gave me this matrix here. The second part is obtained in the same way. But now the order is swapped between these two. So in positions of the identity matrix, so diagonal 1, 1, and 1, I should insert this guy 3 times. So here it stands for the first time. This is 1, 0, -1 from here. Then it stands again here. And then it stands again here. So in this way, one finds the representation of J3. So J3 is a nice and diagonal matrix. So of course it's pretty trivial to just add these matrices. Then we need to find the representation of J minus as well. J minus in the product representation. So we use then the direct product rule for how to obtain matrices again. So we have the representation of J minus times the identity plus the identity for the other representation. So for the first representation times J minus for the second representation. In this case, we're treating two spin ones. So this guy and this guy have the same form. And if you recall, J minus was some matrix that was 0 on the diagonal, and then it had ones one step below the diagonal, and the J plus had ones one step above the diagonal. And then it was a normalization, and that normalization was root 2. So we have root 2s everywhere. Okay, so what we do then is that we take this matrix, and here we insert this big 1, so we have this block here. And again here we insert this 1, so we have this block here. So this is then the representation of this part of the expression. And then we add the other part of the expression in the same way. So however, now we act with the identity on the first representation and with J minus on the second representation. So we have the identity. So we should have this matrix multiplying 1, 1, 1. So we have something here, here, and here. And everywhere we have exactly this matrix. So we have that matrix in the 3 diagonal ones. That is there, there, and there. Now, this implies a 9 times a 9 matrix. So it's a bit cumbersome, but it's not that hopeless, of course, because most elements are 0. So it is not. Okay. First of all, it is fairly easy to. Okay, we want to obtain j squared. So first we should. So j3 we already had. That guy we had up here. It's a diagonal matrix. Then we should have j3 squared. That is also easy. It's just this diagonal matrix squared. Then we should have j minus, which we now spend some effort calculating, times j plus. Now j plus is obtained by j minus transpose. Okay. So I'm not going to do the algebra, but it is straightforward, and one obtains this matrix here. So it looks pretty big. Well, it is 9 by 9, but it has a lot of structure. And we can analyze now the eigenvalues of this matrix. So first, if we have a look at it, we immediately see that we have an eigenvalue standing there and an eigenvalue standing there. So it has the eigenvalue 6. And then to find the other eigenvalues, it takes some computations, but it turns out that the eigenvalues are 6, 2, and 0. So this then, of course, corresponds to the total spin being 0, to the total spin being 1, and to the total spin being 2. So in general, we have j times j plus 1. So 2 times 3, that gives us the 6. 1 times 2, that gives us the 2. And 0 times 1, that gives us the 0. So we have then what we expect. And this is then what we should obtain in the light of this decomposition that Nicolina did before. So we had seen that we had these states here with 5, 3, and 1 jz value corresponding to j2, 1, and 0. So that's then as it should be. Okay, so now we want to find the states. We want to identify the states in the direct sum representation rather than in the direct.
How exactly did you find the eigenvalues of that matrix?
No, I didn't go through the details in finding the eigenvalues of the matrix. But you can see that you only have to find the eigenvalues of this matrix. And nevertheless, that takes some analyzing, but you can see that it's fairly sparse. So for example, from this first column, I can only pick the 4 and the 2, etc. So it's not trivial, and I'm not doing it, but it's not as horrible as it would be if it would be a more dense matrix. Okay. So now we want to identify the states. So luckily, there are 2 states that we can readily identify here. So we know that the state with maximal z value must correspond to the state with maximal j value as well. And to obtain the maximal z value, we just add the maximal dz values in the different representations. So in this case, we add 1 and 1, and we obtain 2. So for the j equals to 2 representation, having 5 different states, that jz2 we can only obtain in one way, by taking the maximal j here and here. So this state we know cannot be anything else but the direct product of this 1,1 state and the other state also being in 1,1. And here there is a prime to indicate that this is the other state. Otherwise I could take the order of them to indicate it, but there is a prime here as well. Okay, so this state must then correspond to one of those two. But we want then to find all the other states in the J2 multiplet, and to find them we act with J minus on this state as we did in the lecture. So we act then with J minus on this side, and we act also with J minus on this side. So first, if we act with J minus on this side here, we call this formula for coefficients. So it was J times J plus 1 minus M times M minus 1 raised to the power 1/2, so square root. So we have 2 times 2 plus 1 minus 2, because we have the maximal M here on this side, times 2 minus 1. So this is 6 minus 2. So that is 4. So we have square root of 4. So that goes into that 2 standing here. So now we have acted with J minus on this side here. That was easy because we had just one representation here. Now we should also act with J minus on this side here. So acting with J minus on this side here, we act with it on one of the spins at a time. So it's J minus on the first state plus nothing happening to the second state plus nothing happening to the first state times J minus acting on the second state here. Now we must know J minus, and we have a little a lucky case here, because if we go up and look at J minus, we have it. We found that everywhere where it's non-zero, it's a factor of root 2. So that is nice. That makes it easier because we have an easy time remembering the factors, and the times where we get something is all the times where we get something that adds up to the correct spin. So it should not be as hard as in some other cases to act with J minus. Okay. So first then we act with J minus on this spin 1. Well, then this jz, which was 1, goes to 0, and we have a factor of root 2, and this state just moves here, so nothing happens to it. Then for the second term, where we acted on the second spin, this spin just stands, and we have acted with the lowering operator here, so this 1 went to 0 here. And the root 2 came because we always had a root 2 everywhere. So now to get this state, we just divide with this factor 2 here. So we have 1 over root 2, and then this linear combination is just copy pasted down here. So now we have found this state, so 2 out of 9 states. Okay, it's not summer we are going to get someone can get easier. But it's actually it's a bit tedious, but it's now the same exercise again. So now we want to find the state to 0. So we act with j minus again, and we act with j minus both on this side and on this side. So acting with j minus on this side, we know this gives us a coefficient. And the coefficient was j, so 2 times j, 2 plus 1 minus m, in this case 1, times 1 minus 1, so that's 0. So we have here just this factor, that's 6. So we have a factor root 6. So this root 6 ends up standing there. Then, let's see what more we have. Yeah, then we have to act with the lowering operator. So it's the same game as before, but now we have more states to act on. So first, we act with j minus on the first state here. And then nothing happens to this state. And then also from this first line, nothing happens to the first state. And we act with j minus on the second state here. Plus another line corresponding to the other state. So again, we act with j minus on the first state there, times nothing happening to this state, plus nothing happening to this state. And there should be a j minus here. J minus acting on this state there. Now, actually, okay. One way of doing this is to do what I'm doing here, and that is to see, well, what do I get when I act with j minus? So what do I get? Here I act with j minus. Well, okay, I get this 0 going to minus 1 here. Here I act with j minus on the second state, so this state stands, and this 1 here goes to 0 there. And then I do the same thing for the other states. J minus on this state. So this 1 goes to 0, so I obtain this state. And the other state just stands. And here I have another j minus acting on the second state. So here, this state goes here. And this is changed, so the 0 becomes the minus 1. So here I know what the j minus operator does to the state. That's one way of thinking about it, but I could actually also have identified all these product states as basis vectors in my new basis, and then acted with this 9 by 9 matrix j minus. So it's either that or doing what I'm doing now. And what I'm doing now is perhaps possibly less error prone. But perhaps also more tedious. Okay, everywhere I recall that I had this root 2, so I'm cancelling off that root 2. That is why it has disappeared. And then I had this state obtained in 2 different ways, because in a sense there were 2 different routes for going down from the maximal state to this state. Whereas this state could only be obtained in one way, and similar, this way could also only be obtained in one way, because in both cases, starting from they said 1, 1, 1, and 1, in both cases one had to act with the lowering operator twice on the same state, here for the first state and here for the second state. Whereas to obtain 1, 0 and 1, 0 for the second state as well, one could go down in 2 different ways. So we have this factor of 2 here. Okay, then the state is then obtained by just dividing out this 1 over root 6. So the state, here it goes, it's 1 over root 6, this thing here, copy pasted down there. And then we continue this. So we continue going down. So now we are acting again with the minus on the state. So it's the same game again. So we have 3 different starting states here. And in each case, for example, for the first line here, we act with the minus either on the first one here or on the second one here. So it's the same thing for this guy, and this guy. Okay, so let's explore at least the first row here. So here we act with the minus on this state, and this state stands. Then we act with the minus instead on the second state, so over here, and this state stands. But now things are slightly simplified, because now we note that for spin 1, the minimal spin Z is -1. So acting with the minus on this state, we get 0. So this guy disappears. Similarly, from this state, when the minus is acting on this spin here, so we have the minus on 1, -1, we get 0. So this disappears as well. But the other states give us something. So from this term, we have the spin, the d minus acting on this guy. It goes over there. From this term, where we have 0 here and 0 here, we can act with the minus on both of them and get something non-zero. So here we have the minus on the first state. Then we have the minus on the second state here. And here from the last state, we only get something non-zero if we act with the minus on this state here. So this is what's happening here. And the other state which is acting on the second term gives us 0. Okay, so now we can collect pieces here. And so I've highlighted in green and blue what's going on here. So here we should add up to spin 0 now. So here we have, sorry, after acting with a minus, we should add up to spin -1. So this will then give us 0, and this will give us -1. So this state goes here. This state, also we have a 1 -1 there. And this state stands, so this state goes here. And then we have this state here, which will give us a -1 here, so it goes there, and similarly this state goes there. And again, we have calculated the normalization, which turns out to be √6, and then to obtain this state, we divide, of course, with the normalization. So we are left with this factor here over √6. So it's 3 times √2 over √6 squared. So it gives us 1 over √2, and the state that we want. So now we have stepped almost all the way down. We should step down one more step. So we should get to 2 -2. And now it comes to a point where I'm not doing the details. I hope you have gotten how it works. And in this case, there are some zeros again to cancel out, and actually now things must start becoming simpler again, because actually we know that there's only one state which has -2 here. So we obtain this state, and actually after cancelling the normalization factors, we see that the 2 - 2 state is exactly this state. And here it comes to a point where I think that some of you are maybe thinking, couldn't we write down that already? Because we know that it must be the case. You're completely right. So in a sense, this piece of algebra here was unnecessary. And as a matter of fact, the second to last piece of algebra as well, going down from spin 0 to spin -1, was also a bit unnecessary. The reason why is that we could have it from symmetry from the spin +1 instead. Okay, so what do I mean with this? So maybe it's easier if we summarize what we have learned so far. So far we have looked into the 5 plet of things. Please feel free to ask questions when things are not clear. So we started out from this 2-2 state, the highest state, and then we walked down to the middle state, which was also the most lengthy state, and we stepped down, and then we stepped down. So this state we got for free, but we could equally well have said that we get this state with -1s here instead of +1s for free. So we could have started from here. Then if we had started from the -- state, and we had stepped up with the plus operator instead of starting from the 1-1 and stepped down with the minus operator, we should have had the corresponding state. So this state here can be obtained from this state here by symmetry. So in fact, it was only strictly necessary to do this step and to do this step. These could have followed. Okay. The conclusion so far then is that after this long exercise, we have found all the states in the 5 plets. So we have found 5 out of 9 states. Then we should have a triplet corresponding to spin 1. And here we do what we did in the lecture. We take the spin 1-1, so triple spin 1, spin Z1 state. There's a 3 here to denoting that it's the new triplet, overall triplet representation. And since the spins here should add up to 1, we know that we must have some linear combination of the state with spin 0 and spin 1, and the state with 1 and spin 0, with some coefficients A and B. To find the coefficients A and B, we use that this spin 1 state should be orthogonal to this state here. So highlighted in yellow here. This state should be orthogonal to that state. Now, that is pretty easy to arrange because here we see that we have this guy plus this guy. So if we just take this guy minus this guy and normalize, we obtain a state that is orthogonal. So we then obtain the highest state within the 3 triplet representation. So we take A is minus B is for normalization purposes then 1/2. Okay, so then we have obtained the highest state in the triplet representation. Then it's the same exercise again. So again, it's a matter of acting with the minus operator both on the left side and on the right side. On the right side as a product to obtain the state with 1-0. So we get this state. after normalizing. Looks like that. And then to find the minus one state, we can either act again with the d minus operator, and that is what is done here, or we can say that we could obtain it from symmetry from the 1 state. Okay, so here it stands in any case. So in this way, we can find all the states in the triplet representation. So it's the 1, 1 state, the 1, 0 state, and the 1, minus 1 state. And now if we have a look at this actually already, we note that this state here is antisymmetric with respect to exchanging the two states. So with respect to exchanging the first and the second guy, it's antisymmetric because this state here will then be mapped into this state here. And they come with a relative minus sign. So it's antisymmetric with respect to exchanging the two participating spin 1 states. And if we look at it, we see that this antisymmetry is following. So this state is actually also antisymmetric. So if we swap them, this guy goes to this guy, and this guy goes to this guy. So we get the same thing, except for that we get a minus sign. And similarly down here. So actually all these states are antisymmetric with respect to exchanging the two spins. Whereas if we take a look at what we had before here in the 5-plet state, this is of course trivially symmetric because we have the same thing here and here. So exchanging them, nothing happens. We get back exactly the same thing. And this is also symmetric, and they are all symmetric, and they are all symmetric because the symmetry is preserved when we act with the step operator, as the step operator acts in a symmetric way, either on one of them or on the other one of them. That is related to so we see here that the symmetry is something that is the same for all the states in triplet state or all the states in the 5 state. And this is actually related to the more systematic ways of finding multiplets in general. So we have seen how to do it for SU2. We can also do it for SU3. We have in principle seen how to do it, although it was quite quick. We had this 2-dimensional root planes, and we added the states together by laying them on top of each other. Actually, was pretty much the same as we did here in this case, but it was just a 2-dimensional exercise instead. If we would have more than 2 dimensions, we would exhaust the dimension of the paper, and we could imagine that it would be a mess. But in any case, for SU2, for SU3, and for higher SUs as well, one can use Young tableaus, and I'm not quite sure how much I will have the time to speak about them, but their point is to systemize the use of symmetries to get multiplets and to get representations. So with those, one can get the representations in a quicker way and in a more general way than what we have seen so far. Okay, so let's get back to topic. We have found the triplets. So now we have found the triplet representation. We have found the 5-plet on spin 2 representation. So we have found 5 plus 3 equals to 8 states, and we should only have 1 state remaining. So that is then the state in the spin 0 representation. And that state we can again obtain by taking a linear combination of states with spin adding up to 0. So -1, 1, 0, 0, and 1, -1. And then we want this to be orthogonal to both the total spin 2 0 state and the total spin 1 0 state. And that then gives us a little equation system to solve. And after solving it, one can find that the state should look like this. Then the next question, let's go on and read it so we know what we're trying to do here. So we have find the states in the irreducible multiples corresponding to the eigenvalues of A square and how they are related to the original states. Yes, we have essentially done that, but we haven't written down the matrix. So now we have found, in principle, we have found a relation between the original state and the states in the reduced representations, but we haven't written down the matrix. Writing down the matrix is then possibly tedious exercise of identifying the states in the direct product representations with the states in the reduced basis. So we are not going to have time to do that in detail, but if we just have a look at one or few elements here, we see that this state 1 here. So in the direct product basis, the first basis state in the direct product basis is the one where I take the highest state everywhere. So that would be 1, 1 times 1, 1 primed. So this would be my E1 in the direct product basis. But this coincided with one of the states, the highest state, 2, 2. And this equal sign is what gives me this factor of 1 here. Then I can, in similar ways, I must find the relation between the basis states in the direct product representation. So the direct product representation basis states are then obtained by the direct product. So E1 would be 1, 1, 1, 1, as we have seen with the prime there, but I'm going to ignore the prime. And E2, I will go down one step. So this is, I will go down one step for the second state. So this is 1, 1, 1, 0. And E3 is 1, 1, 1, minus 1, etc. And then E4, 5, and 6. For those, I take the state that I have here, but with the 0 here instead. For E7, 8, and 9, I have a minus 1 here instead, and those there respectively. So that would be my basis. And to write down this matrix, I just go and look up all the coefficients. And this matrix, so I'm running out of time, so I'm not doing it, but looking up all the coefficients, one gets that matrix, and that matrix then gives the change of basis between the direct product basis and the reduced basis. And if one would then apply this change of basis, one can apply it, of course, to the states, and indeed we have identified the look of the matrix by looking at the states, but we can apply it to the matrices as well. So if we apply it to J square, we should obtain that J square now has this block diagonal form. So J square in this direct sum representation has a block with J times J plus 1, so that's 6 here, that's 2 here, and 0 here. The next part we have actually already discussed. So the 5-plet is symmetric, the triplet is anti-symmetric, and one can see that the singlet is also symmetric with respect to exchange of the two spins here. And that is not something that that symmetry is something that depends on the starting building blocks that one starts with, and it's not something that is inherent to the representation, because it's a symmetry with respect to the two participating representations. So in this case, the two spin ones that we use to get the total spin 2. It's that sort of symmetry. So it's not related to the spin 1 representation in itself or so. And we are running out of time, but actually what we did in this exercise was, to a very high degree, a repetition of what we did in the lecture, but with other spins. So I think it's time to finish now, but let's see if there are any questions. So it was a fairly lengthy exercise, this one, but it's a good exercise. For the next exercise session next Friday, I should make, now when we are done, I should make the exercise sheet available. And if you don't manage to solve the exercises, it's useful if you let me know in advance, because then I am a bit better prepared and I'm probably making a better presentation. But an even better outcome would be if you ask me and I help you such that you can present the problem. Okay, so if I have no questions, I'll say thank you for today and see you on Tuesday again. Of course, you can also ask me questions now when most people have left. So Edmund or Victor, did you want to ask something? Okay, so Edmund, if you have no questions, I would actually suggest that you leave, because me and Nikolai have other things to discuss. So then I'm saying bye to Edmund by actually removing you, because you were not asking any questions. So I think maybe you're not even in front of the computer, and me and Nikolai have things to discuss. So bye. So I never removed anyone before. It says he won't be able to rejoin. I hope it just applies to this time. Otherwise, it would be quite nasty. I know what I do. I put him in the waiting room instead.
Smart.